In the beginning, there was nothing, or so it seems. No stars, no galaxies, no planets, not even time or space as we understand them. Yet, from this enigmatic void, the universe as we know it emerged, a tapestry of light, matter, and energy stretching across 93 billion light-years. The question that has haunted humanity for millennia, how was the universe created, is not merely a query about origins, but a journey into the heart of existence itself. Today, we embark on an exploration grounded in the most rigorous scientific discoveries, peering into the crucible of cosmic birth, guided by the light of reason and evidence.
The story begins approximately 13.8 billion years ago, in a moment so singular it defies comprehension, the Big Bang. This is not an explosion in the conventional sense, scattering debris into a pre-existing space, but rather the rapid expansion of space itself, a moment when all matter, energy, space, and time burst into being. The term Big Bang was coined by astronomer Fred Hoyle, somewhat tongue-in-cheek, yet it has become the cornerstone of modern cosmology. But what does science tell us about this primordial event, and how do we piece together the evidence for such an audacious claim?
The Big Bang theory rests on three pillars of observational evidence, each a testament to the universe's dynamic history. The first is the expansion of the universe, discovered by Edwin Hubble in the 1920s. Observing distant galaxies through the 100-inch telescope at Mount Wilson, Hubble noted that their light was redshifted, a phenomena where light stretches to longer, redder wavelengths as objects move away. This redshift revealed that galaxies are receding from us, and not just receding, but doing so at a rate proportional to their distance. The farther the galaxy, the faster it retreats. This observation implies that the universe is expanding, like the surface of a balloon inflating, with every point moving away from every other. If we rewind this expansion backward in time, we arrive at a single point of infinite density and temperature, the Big Bang.
The second pillar is the cosmic microwave background, or CMB, a faint glow of radiation permeating the universe. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, this relic radiation is the afterglow of the Big Bang itself. In the universe's infancy, it was a searing plasma of protons, electrons, and photons too hot for atoms to form. As the universe expanded and cooled over 380,000 years, electrons combined with protons to form neutral atoms, releasing photons in the process. These photons, stretched by the universe's expansion, now appear as microwave radiation, with a temperature of just 2.7 Kelvin above absolute zero. The CMB is remarkably uniform, but tiny fluctuations in its temperature, mapped with exquisite precision by satellites like COBE, WMAP, and Planck, reveal the seeds of structure, the embryonic clumps that would grow into galaxies and galaxy clusters.
In the beginning, there was nothing. No stars, no galaxies, no planets, not even time or space as we understand them. And yet, from this enigmatic void, something extraordinary happened, a flashpoint of creation, a moment so profound it gave rise to everything we now know: light, matter, energy, and the very fabric of reality. This is the story of our universe. Roughly 13.8 billion years ago, the universe sprang into existence in an event we call the Big Bang. But this was no explosion in the traditional sense, no detonation into empty space. Rather, it was space itself expanding, an eruption of existence where all of time, matter, and energy began. The term Big Bang was coined somewhat playfully by astronomer Fred Hoyle, yet it remains the cornerstone of modern cosmology. So how do we know this happened? What evidence supports such a colossal claim? Modern science rests its case on three foundational pillars, each a powerful testament to the universe's dynamic origin. First, there is the expansion of the universe, discovered in the 1920s by Edwin Hubble. Using the mighty 100-inch telescope atop Mount Wilson, Hubble observed that distant galaxies were redshifted, their light stretched to longer, redder wavelengths. This revealed something astonishing. Galaxies aren't just drifting away, they're racing from us at speeds proportional to their distance. The farther the galaxy, the faster it recedes. This suggests that space itself is expanding, like the surface of an inflating balloon. And when we rewind this expansion in time, we arrive at a singular point, the Big Bang. Second, there's the cosmic microwave background, or CMB, the afterglow of creation. In 1965, Arno Penzias and Robert Wilson stumbled upon a faint hum of radiation coming from every direction in space. This wasn't interference. It was a whisper from the past, a relic of a time when the universe was a searing plasma of protons, electrons, and photons. Roughly 380,000 years after the Big Bang, as the universe cooled, these particles combined to form neutral atoms. Light was finally free to travel, and that ancient radiation still bathes the cosmos today. With a temperature just 2.7 Kelvin, it carries subtle fluctuations, mapped with stunning detail by satellites like COBE, WIMMAP, and Planck. These tiny imprints are the seeds of galaxies, the blueprint of cosmic structure. The third pillar lies in the abundance of light elements. In the first few minutes of existence, the universe was imaginably hot, billions of degrees. This allowed fusion to begin in a process called Big Bang nucleosynthesis. Protons and neutrons collided, forming the nuclei of light elements, primarily hydrogen and helium, with traces of lithium and beryllium. The predicted ratios, about 75% hydrogen and 24% helium by mass, have been confirmed by studying the oldest stars and ancient gas clouds. This elemental fingerprint is a direct echo of the universe's earliest fire. And yet, behind these pillars lies a deeper mystery. What came before the Big Bang? Here, science enters the realm of speculation, still grounded in theory, but beyond the reach of direct observation. The Big Bang is not the beginning of everything, rather the boundary where our current physics becomes meaningful. In the unimaginably short Planck epoch, the first 10 to the minus 43 seconds, the universe was so dense, so energetic, that the known laws of physics collapsed. Quantum effects dominated, and space and time themselves blurred. Some theories propose that the universe emerged from a quantum fluctuation, a sudden disturbance in a pre-existing vacuum. Others suggest a cosmic bounce, where our universe is the rebirth of a previously collapsing one. String theory and loop quantum gravity offer tantalizing frameworks, but without observational evidence, these remain educated guesses. Then came a turning point: cosmic inflation. In the blink of an eye, around 10 to the minus 36 seconds after the Big Bang, a hypothetical field called the inflaton drove the universe to expand exponentially. In less than 10 to the minus 32 seconds, the universe grew from subatomic to macroscopic scales. This explosive growth flattened space, erased irregularities, and seeded the cosmos with quantum fluctuations, microscopic variations in density that would grow into galaxies and clusters. Inflation helps resolve key puzzles. Why is the universe so flat, not curved? Why do regions billions of light years apart look so similar in temperature and structure? Inflation stretched space to cosmic scales, smoothing it out and ensuring uniformity. Though we have not yet directly detected the primordial gravitational waves inflation should have left behind, observations of the CMB support its predictions with remarkable precision. As inflation ended, the universe reheated. The inflaton's energy decayed into particles, quarks, gluons, electrons, and photons. By 1 second after the Big Bang, the universe had cooled to around 10 billion Kelvin, dense with radiation and matter. For the next few minutes, light elements formed through fusion. And then, for hundreds of thousands of years, the universe remained an opaque plasma, a fog of scattered light. At 380,000 years, a crucial threshold was crossed. As temperatures dropped to 3,000 Kelvin, electrons combined with protons to form neutral hydrogen atoms. Photons were finally set free, streaming across the cosmos to become the CMB, our most ancient cosmic image. With transparency achieved, gravity began to sculpt the universe. Those tiny inflation-born density fluctuations pulled matter together, forming stars and galaxies. By 100 million years, the first stars ignited. Massive, luminous population 3 stars made almost entirely of hydrogen and helium. Their radiation reionized the universe's gas, ending the cosmic dark ages. This epoch, known as reionization, set the stage for the visible cosmos. Galaxies formed into filaments and voids, shaping the cosmic web. Guided by dark matter, an invisible force that makes up roughly 27% of the universe, these structures grew vast and intricate. Though dark matter cannot be seen, its gravitational influence is undeniable, warping light, binding galaxies, and anchoring the universe's structure. Then, in the late 1990s, came a stunning revelation. Astronomers studying distant supernovae discovered the universe wasn't just expanding, it was accelerating. A mysterious force, dark energy, is pushing galaxies apart at an increasing rate. Making up about 68% of the cosmos, its nature is unknown. Is it a cosmological constant, a dynamic field, or something stranger? We don't yet know, but it dominates our universe. Dark energy shapes not just the present, but the future. If it persists, galaxies will drift beyond visibility, stars will extinguish, and the universe will grow cold, dark, and empty. Some models predict a big rip where even atoms are torn apart. Others suggest a steady, eternal expansion. Projects like the Dark Energy Spectroscopic Instrument are now racing to uncover its secrets. So, how was the universe created? This question, once the domain of myth and philosophy, is now the frontier of physics and cosmology. From Hubble's redshift to the CMB's whisper, from primordial hydrogen to dark matter's invisible web, we are decoding the story of everything. And yet, the mystery endures. What triggered the Big Bang? What is the true nature of dark energy? Is our universe one of many? As we build new instruments like the James Webb Telescope, the Vera Rubin Observatory, and future gravitational wave detectors, we look deeper into time than ever before. One thing is clear. The universe is not static. It's a story still unfolding, a cosmic epic driven by emergence, complexity, and wonder. And we, curious children of stardust, are just beginning to understand the first chapter.